So hi everyone, and welcome back to the final installment of the 2020 University of Alberta Geotechnical Graduate Student Seminars. I'll start off by just reminding everyone that there's another great presentation being held tomorrow at noon by the Geotechnical Society of Edmonton. At this event, Dr. Amir Hagi, the previous winner of the Morgenstern Award for the Best Graduate Students presentation, will be presenting on a novel semi-analytical model that was developed to study the influence of stress-dependent effects on porosity, absolute permeability, relative permeability, and capillary pressure on the imbibition of oil recovery mechanisms of both intact rock and fracture in cubic block models. Please come out and support and listen to him tomorrow for his great presentation. As this is also our last presentation of the year and the first time that the U of A has completed the graduate seminars virtually, I thought I'd give a shout out to all the people that have been working to put this together. First, of course, we have our tireless leader, Vivian Zhang, who has been making the seminars a success for many years now. Then there's also our behind the scenes team, which includes Fernanda Imamura, Aiming Liao, and Nabil Islam. And of course, our Q&A mediator, Lang Liu. So thank you all for your hard work with this. And all right, so today we have another very special presenter in Dr. Gord McKenna, who will be speaking on the designs of tailings landforms. Dr. McKenna is a geotechnical engineer and geologist who is in the business of building mining landforms and watersheds. In fact, he and his team have designed and built 23 reclaimed watersheds that cover over 44 square kilometers of land, host 37 wetlands, and 101 kilometers of streams. Dr. McKenna is not only a builder, but he's also a teacher. He's an adjunct professor in the Civil and Environmental group here at the U of A lead contributor to several manuals involving landform design, mine reclamation, and tailings, has co-authored more than 100 technical papers, and has led over 40 landform design courses. His specialties include mining geotechnique, tailings dams, soft tailings, and landform design. Please join me in welcoming Dr. Gord McKenna.
Thank you very much, Kevin. I've got my first slide up here. It's a pleasure to be back speaking to the students at the university and others who've joined from the Edmonton Geotechnical Society. When we last talked, some of you may have been in the lecture in the spring, where we got into some of the details and backgrounds of landform design. This time we're going to turn it into a more practical how to design tailings landforms. And introduce you to, we'll cover some of the concepts and that, but we're going to launch into a list of difficulties in dealing with tailings and in reclamation and regrading of them generally. And so we've got 18 of those coming up with solutions, problems and solutions together. Now, these are based on a paper that Dirk Van Zyl and I put together last summer that I'll show in a couple minutes. It follows closely. Dirk hasn't actually seen this presentation, so don't hold him to any of the details, but it's drawn from our paper. And it's part of the compendium that supports the Global Tailings Initiative and is available online. I should also point out Daryl Shuttleworth, some of you'll know, or at least recognize his artwork here, and he's done all the illustrations for this. His contact information is available on the last slide, and I'd encourage you to get him involved in your upcoming projects as a technical illustrator. I should say Daryl and I have worked together for about 25 years and done work for dozens of mines. So times they are a-changing again, and this is one of the sort of overarching messages for this Graduate Students Association. Along the bottom here, I've shown tailings dam failures, the number per year. This is from the Wise Uranium website, and you can see a fairly steady number, typically 1 or 2 major tailings dam failures per year. At least these are the ones in the database. There's actually quite a few more, I think, than are shown here. But you'll also see every now and then the numbers spike, as you might expect, perhaps with a uniform distribution. You may also, there's a hint there that more recently that there's been more. It's kind of a denser graph on the right-hand side. But there's also been very, very many more dams. If we go back, there's a couple moments just to point out that make for nice history, and I encourage all of us in the profession to really understand the history and where we've come from. Oftentimes we get a little bit focused on sheer strengths and learning our trade, but I think it's important to step back and understand some history. There's some good biographies of Terzaghi and that you can tap into, for example. But one of the major historical points, 1966, is the Aberfan disaster in Wales. There's a coal waste rock dump, a tip they would call it, that flowed out into the village and killed over 100 people, including flowed into a school and killed over 100 people, including an awful lot of school children. And it was that time there's a major shift. There's an inquiry and a major shift, and I would argue it became the new era of geotechnical engineering, especially in mine waste management, where they started to require geotechnical engineers, professional engineers, to sign off on such facilities to reduce these kinds of risks. This isn't a tailings failure, but it flowed as similar to being tailings in some ways. And the point that affects all of us here today is that this is when most of the large international geotechnical consulting firms started in response to better engineering of such structures. And yet, here we are 50 years. I was born in 64, so, more than 50 years on, and we're still having major mine waste facilities and notably, or failures, and notably tailings. So Brumadinho here is in the other picture, 2019, sudden static liquefaction. Many people from the university and graduates and ex-professors at the university were involved in the investigations behind that. And this marked a really seismic change in tailings. I don't think any of us really recognize just how much times are changing for the tailings. I've been involved this last week in a risk assessment for a mine in the Caribbean that has a very large tailings dam. And it's being analyzed under this new standard, this global industry tailings standard management. And essentially what's happened is the investors have stepped in and said, look, we're not accepting of this rate of failure anymore. Having one or two a year, the professions aren't doing their job, the regulators aren't doing their job. And so they banded together and put together this new industry standard. And there's a lot of really new stuff in there that's affecting our practice, including risk assessment. And really, I think they want us to really reduce the risks by an awful lot. And we go through these risk assessments and we'll often say, oh yeah, that's fine. We've designed against that. Yeah, things are good. But continuing on in our current state of practice isn't meeting society's demands. And so this is a major seismic change. It will affect quite a lot. I should note also that the focus has been, and probably will be for the next 5 years, on changing the governance models and who's responsible for what and audits. And it's going to get out of control if it already isn't with the number of audits. There's one mine site fellow I was talking to said, yeah, there's 5 or 6 sets of audits every year on our facilities. And that's not very efficient or sustainable, but maybe it's part of the new paradigm here. There's not as much focus, I don't think, or enough focus on good design. And I think that's fundamental, that we need good design here. So that's what we're talking about today. As the Global Tailings Standard was coming out, there's a compendium put together, and Dirk Van Zyl and I were asked to put together a closure and reclamation chapter. In support of this, people are recognizing the importance of closing stuff so that it's stable, and also a lot of closed facilities revert back to the Crown or the state and can cost billions of dollars to fix. And so these are another kind of failure is lack of reclamation or lack of making good landforms that are useful for people to come and use. When we were asked to do Chapter 8, we responded, Well, I responded, hey, we should be chapter 1. Why are we got to wait till chapter 8? If you do closure and reclamation, you're always at the end. You're always Friday afternoon at conferences, the CIM or other things, and even the courses we teach, we tend to be at the end. But really, most of the decisions to do with long-term stability of the tailings over the next 1,000 years, to do with land uses, to do with technology selection, they're all made actually before mining even begins. And so people aren't ready to let us be chapter 1 or chapter 2 just yet, but designing with the end in mind is starting to be recognized as an important aspect. We've kind of known this for about 40 years, but we're still teaching ourselves. So tailings, most of you will know about tailings, but I'd like to just make sure that we remind ourselves what they are. This is typically the ground up rock, the ore that from a metal mine or a coal mine, and the metals or coal have been liberated from the rock, and this is the crushed up rock that's left over. Oil sand tailings, some of you that are shown in the pictures here will be more familiar. It isn't actually crushed so much. It's more just had the bitumen liberated from it, and it's more natural sand. But it turns out most mines have pretty small tailings facilities. Most mines, they settle fairly quickly. And it isn't really an issue. It's just if you have clay in your tailings, then you end up with like these oil sand situations. But let me come back to that as we go. When I presented, many of you have been in that lecture last spring, all this before stuff. We discussed landform design in detail, and let me just give you a bit of a recap of how this landform design business works. It is an addition to the geotechnical and dam design work and tailings planning that goes on anyway at most mines. And it's crafted to follow the Ralph Peck's geotechnical observation method you'll recognize in here from 1969. The first step is forming the landform design team, kind of shown in the cartoon in the right, bunch of different ologists and different people in them. The team's typically anywhere from about 6 to 12 people, includes geotechnical, surface water, groundwater, geochemistry, soils, veg, wildlife, ideally includes First Nations work or people on the team, management, mine planners, you name it. It's quite a big group, a little bit unruly. There needs to be a lead designer, like a single person who's in charge of the design. The second box there on the upper right, you establish the governance, and this is often a steering committee, or it might be the mine manager or the chief engineer at the mine oversees the work of this. The team creates a design basis memorandum that's coming up in one of the slides here. This is the vision, the goals, the design objectives and design criteria, just like we would do for a building. This is also set out for landform design. This is something that's been done since 1980s, but isn't done for most reclamation. It's a bit of a change.
Hey, Gord, I'm just going to jump in here. We're seeing one slide off of what you're talking about.
Oh, I appreciate that. That's my fault. There we go. Thank you. Appreciate that, Kevin. So we're working through the flow slide at the right. We're into the yellow box then on designing the landform. This is where a bunch of work, and a lot of what we're talking about today is fairly qualitative and fairly general, and there is a certain amount of that to landform design, but there's also supercomputer work and complex environmental models, seepage models, you name it. There's quite a lot of work and a lot of sort of rocket science that goes into it, but most of what we're doing is fairly easy to understand and straightforward. Go through and assess the risks with your design. Typically an FMEA process is used. And then crucially, you'll do design contingencies. And this is where some other methods of design like adaptive management and trial and error don't really work, is that we need actual contingencies. And this comes out specifically out of Ralph Peck's work. And so the contingencies, if things aren't working as well as the design as you're building it, that you have actual contingencies that are actually planned and costed and certain level of design, quite a high level of design usually, and can be implemented in a timely manner. You go through and construct your landform, which is mostly the bulk material placement. In the case of tailings, it may be slurried out or trucked out. And this is where 99% of the material, this bulk landform stuff, is going. It needs to be done well, but it's typically fairly low spec. You will monitor the performance, and if performance is good, you continue. Otherwise, you may be changing how you do your construction. You know, if something doesn't pass a compaction spec, of course, you're going to go back in and recompact it. If the tailings aren't performing as intended, you might go all the way back and change your design or change your tailings technology. If things still aren't working well, you might go all the way back, as the arrows indicate on the right there, and change out your governance team if you're not doing it properly. You're going to implement your contingencies there. The second lower box is needed. And then this is what the Eurocode added, is adding in an annual audit. This will often be done by the review board. Let me set out a couple things that the Landform Design Institute is working on. We formed the Landform Design Institute 1 year ago, helping to take this notion of landform design that started with Dave Seago and Nordy Morgenstern, professors at the University of Alberta, asking me to start a master's and eventually a PhD into developing this concept. This is back in the 90s. We've been practicing for 25 years and trying to make it a more global phenomena so that others can benefit from it and teach us about it. And so we developed the Institute. 1 year ago, we've got a board and technical advisory panel members. And then the last slide that I'll show you here today is your chance to join the mailing list or sign up for $10 as student members and take part in the Institute's work. The Institute is trying to do some redefining of a few things. We'll see if we're successful or not on this one. The new timeline of mining. Mining, we're saying, runs through a period of pre-mining, of exploration and planning and design, construction or development, sometimes it's called, of building the starter dams and building the mill site and that. And then operations is the main piece, and we've added in operations of progressive reclamation. This is ongoing reclamation that occurs while mining and tailings deposition is going on. Then you kind of get to the end, this mine closure. Most people think of mine closure as towards the end of a mine and forever on, but we're defining it here as a point in time, an actual day that the end of ore mining or the end of ore milling occurs. And that's closure. That's when there's typically huge layoffs and the mine site shifts fully into final reclamation, or decommissioning is shown here, and closure and reclamation. And then it moves on into a period of aftercare where it's being monitored and maintained. A lot of miners still think that we'll walk away from the sites, as we'll talk about in a couple slides, but essentially for most mines, there will be aftercare that runs for decades, if not centuries, if not forever afterwards, as we'll describe in here. So this is a bit of a new terms and or redefining of the terms. Now these apply for a whole mine site that would have quite a few mining landforms, like tailings ponds, one or more waste rock dumps, one or more mine pits, mill site, various other landfills and different things that are useful to think of as mining landforms. But it can also apply to an individual tailings facility that we're focused on here today. And so when the last tailings goes out and the pipeline shut off, that can be thought of as the closure of that facility. And then we can launch into the decommissioning, post-reclamation, and then into the aftercare. I think I'm having some problems with some of my slides here and what's showing. I apologize. I'm just getting mixed up between my screens. So there's some misconceptions that have come out over the years about landform design, especially to do with tailings and more generally. And the Landform Design Institute is trying to rise to this challenge by producing a report, a position paper in the new year that cleans up some of these misconceptions, according to us. And one of the, there's a list here. What are the things that I've heard over the last couple months, mainly in all this new tailings global initiative stuff? People are especially interested now in improving their tailings management, and these are the kinds of things I hear from people, mostly geotechnical engineers, mostly people and mine managers that aren't involved in all that much reclamation, but are keen to learn. And they will say things like, and I hear all of these things all the time, we only need a conceptual closure plan. And we'll discuss this in a couple minutes. But everyone has, for 20 years or so, has taken pride that the closure plan for the mine site only needs to be conceptual, a couple pages, a drawing, a sketch, and that will suffice. But it turns out that the closure plans actually need to be detailed enough, and our landform designs, even before mining starts, detailed enough to make good decisions on. And we'll discuss how to do that. They say, don't worry, Gord, we'll turn this tailings facility into a landform after closure. And we would argue that it's a landform even before mining begins, or at the very least when the starter dike is built. Landforms are distinct topographic features that together make up the surface of the earth. And so as soon as you're starting to build something new here, we would call it a landform, and then be able to take advantages of all the different knowledge about landforms and all the different ologists who work on it together. It's not something that you can leave until the end. In fact, if you leave it to the end, you've lost all sorts of opportunities. Landform design only applies to greenfield sites. Gord, we'd love to do landform design, but we're already half constructed, so we're not going to do it. Maybe next time. And it turns out in my career, you're almost always coming on to apply landform design principles to something that's already in construction. It's never too late to start. It's better if you start early, never too late to start. Landform design is too new. I was an expert witness last week for a mining project, and the proponent said, Gord, you're really pushing this landform design, but it's too new. It's still experimental, isn't it? We can't really be expected to apply it at our mine. And I'd argue, well, actually, we've got 25 years of doing landform design. It's kind of breaking out on its own around the world, people setting out their goals and doing their designs for this. And it's not whether you need to do it or not, it's an opportunity to use these kind of processes. Landform design is about aesthetics and natural appearance. Don't worry, Gord, we're going to regrade it. It'll look just like the hills in the normal area. And this is true, and it is about aesthetics and natural appearance and form and function and drainage and all that kind of stuff. And we tend to focus a little bit too strongly on the surface materials and the covers and the shapes. But it turns out landform design is also important about the internal structure, about tailings technology selection, about controlling the movement of water and air through tailings and dumps. So it's more than the aesthetics. Landform design costs too much. There used to be a oil filter, Fram oil filter commercial back 30 years ago or so, you know, promoting the people to change their oil filters in their cars all the time. You can pay me now or pay me later. We think landform design saves a lot of costs and allows mines to meet their commitments, but it does require more design effort, and a lot of you will be involved in such teams, larger teams, more work together. Ultimately, needs to save money. We need to do a bit better job of explaining that to the mine managers. The last two, I'll leave it till next year, or progressive reclamation can wait. And we're seeing that mines make promises for various things and then are typically falling behind in their schedule on that. There is opportunities for deferment of some of the work, but typically you want to set a reasonable schedule and follow it. Sorry, this was that new timeline that we talked to. I had the wrong slide up. Just leading through the pre-mining construction operations, decommissioning, and the aftercare, and noting the two vertical bars. The first ore is an actual day, and the mine closure is an actual day. So the heart of the talk then today is providing how-to solutions. The Landform Design Institute was formed largely to provide how-to. In doing that, we'll be putting together several publications a year and providing case histories and different things amongst each other with a real focus on not what to do, but how to actually do it. It turns out there's lots of guidance available over the last 10 years or so, kind of at the 30,000 foot level on how or on what to do, but not very much on how to, and sometimes minds and practitioners struggle with the actual details. So here's 18 sort of problems and solutions. The first one of the problems they're faced with tailings landform design is that we don't have a clear plan. Oftentimes the geotechnical people and the mine planners and tailings people essentially build the landform, do the dam design, do the construction and that, and then it's left for the reclamation people to kind of clean up and remediate at the end. This is what happens at most mines. There'll be a closure plan, so they sort of know where they're going and that, but the design of the final landscape is not done. So the opportunity here then, if you don't have a clear plan, is to design your closure plans, as we talked about a moment ago, at the pre-feasibility or the feasibility level. These are mining terms for levels of design. So not a conceptual closure plan, not just what Daryl has drawn here for a tailings pond with a little wetland in it, but a full-on engineering design at the pre-feas or fees level. This is important for the mine economics as well, and for bonding and financial assurance that comes up, making sure you've got enough soil to do it, making sure people in the community and the regulator buy into the vision of what you're trying to do, and doing enough design so that there's enough detail that any fatal flaws in the design become apparent right away and can be worked. Sorry, I'm messing up on my slides again. I'm just going to change something so I don't do that. Sorry, here's where we're talking about a clear plan. I apologize again. We'll avoid that now that I've changed my monitor setup. Moving goalposts is a major issue. People build these tailings facilities over 10, 20, 30, 40, even 100 years. And the regulatory requirements, professional requirements, and even what's desired by the communities changes over that time. We'd like to think that we had it locked down at the beginning. You can't ask us to change as we go, as we build these things, but we recognize that technologies change, expectations change. And typically mines don't have a design basis memorandum for their tailings facilities. They would have it for the mill site. The mill site will produce 5,000 tons per hour, that it will do this, it will have this kind of recovery, and that it will take up, it'll be a 10-story building or whatever. But we don't have that for mine sites. And so one of the major aspects of landform design is to set out a design basis. This is what we can be held accountable as a design team, that there's a vision of what the landscape's going to look like, shown at the top there, that we would have goals in support of the vision, design objectives in support of the goals, and design criteria in support of those design objectives. So the vision might be, and I've stolen the vision for the oil sands, it's written into people's permits, to build a reclaimed landscape such that the reclaimed soils and landforms can support a self-sustaining, locally common boreal forest. So there's our vision. We're all working towards that. We're not working towards building parking lots. We're not working towards building a brownfield site that we build a new refinery on, we're building this boreal landscape, this boreal forest. One of those goals might be that the landform slopes are geotechnically stable. And this is always a concern because as geologists, we know geotechnically stable is in the eye of the beholder. What if there's one tiny little slump on your landform? What if the whole thing's moving but slowly? So we need to define that. But almost all regulations and requirements require geotechnical stability regardless. So we need to define that. One of the ways in a design objective is to avoid ponded water near the slopes. Geotechnical engineers hate ponded water, especially near slopes. Might get in a crack and blow out the slope, all those kinds of things. And so our objective is to avoid that in support of being geotechnically stable. And then down to the criteria level, we'll prevent water, we'll design the landform to prevent water from flooding into that zone. And we'll talk about how to do that in a moment. One of the problems that comes up is mines are having difficulty in meeting a progressive reclamation goals, that they'll have 100 hectares per year reclaimed every year for the next 20 years and that. And there's a lot of reasons why they're not meeting that, mostly because it's often preferable to defer costs. The diagram here shows some active mining in the right-hand corner, some in-pit dikes being built, tailings being deposited between them, and then reclamation coming in behind. And you can just imagine this over time, the mining keeps going to the right, more dikes get built and the reclamation comes in. So when you get to the end of mining, you might have a half dozen dikes and you've got 2/3 of your land already reclaimed. There's a bunch of, this requires fortitude and prioritization and scheduling. There's something I'm calling aggressive, progressive reclamation, where you work hard, say in your tailings, to make sure that the tailings can be reclaimed in a few years, and you don't keep your tailings ponds limping along with just a few cubic meters a year going out there. You get done, get out and reclaim. The advantages to such a thing is you reduce your long-term liability, but mostly for the design team, you're learning as you're going, you're learning how capping works, you're learning how the trees and bushes are performing, and you can adjust your methods as you go. Also helps explain to the stakeholders, they can come out and see whether they think your reclamation is working. One of the challenges in landform design for tailings is it's hard for the teams to work together. It takes about 3 years for a team to really gel and get to have enough cross training and so that the biologists know what the engineers are thinking, what the engineers understand what the regulator's thinking. And the cartoon here kind of shows that the different people at the table, they all have kind of different priorities. They've got different backgrounds in their training. They're all working towards the same vision. But the geotechnical engineers might be focused on stability. The process engineers on keeping their discharge on spec for tailings. The First Nations want to make sure that the land is safe to use. Each of us comes at these with a different thing. So we need to make sure our design takes care of each of those groups. Mines recognize they need to work with their communities, but oftentimes they don't know how to engage, especially in something like landform design for tailings. In big mines, oftentimes this engagement is kind of farmed out to the public affairs group. And sometimes they don't want technical people talking to local communities or the regulators. We tend to promise too much or agree to things, or we don't know how it's done kind of thing. But I think we need to have these people right on the team, on the design team, and helping us make design decisions. And that if you don't know how to go about engaging with your community, I'd say just ask them, go for coffee, find out how do they want to be involved. Some want to be involved in monitoring, some want to be involved in decision making, some are too busy to be involved and just want to be kept posted. But they're just simply going and asking how they want to be involved is immensely rewarding. Next slide is mines are often have angst that they can't afford the latest tailings technology. This slide comes out of a 2012 tailings deployment roadmap that I was involved with. And it gives the idea that you shop in a cafeteria style for your tailings, that you would, or in your technologies, you'd use certain mining technologies and extraction technologies that affect your tailings. You've got tailings technologies like dry stack or filter tailings or slurrying or co-disposal, all the things that you will have heard of. You'll have reclamation technologies, and oftentimes we need water treatment technologies at the end. And then we have to pay for them all at the cashier here. Oftentimes, and I see this quite often in decision analysis I've been involved with, is that the tailings technology that scores the highest for environmental is often the most expensive and can be 5 times the cost. It can be billions of dollars more for a large mine. And so the mines tend to, that's an awful lot of money. And sometimes I would argue that if you did sort of cradle to grave work, that as they think they're doing in their assessment, that they would understand that these costs may be required. But typically what I'm seeing is oftentimes we pick tailings technologies that meet a whole bunch of operational goals, but are really, really hard to close. They might score 2 out of 10 for closure, but 10 out of 10 for everything else, and they end up getting selected. So what we need to do then is go back instead to that design basis memorandum. What is it that we're required to do in the landscape? What are we promising? And then what tailings technologies can reliably meet that? If you can't meet all your design basis things, you might have to go back and renegotiate them. That's fine. But I'm finding too often we're picking tailings technologies that are very difficult to reclaim. One of the main pushes in this global tailings initiative is to reduce the risk of catastrophic dam failure. And I think most people would have thought until Brumadinho that once you get your dam and your tailings built and you're done, you've got almost no risk of a catastrophic failure. But if we've got semi-stable or mobile materials with rising water tables and that, it shows firsthand that we can have major dam failures even after closure. So where does landform design come in? Landform design looks at all stages, including operations and that. And if we truly want to reduce our risk of catastrophic failure, we've got to reduce the amount of mobile materials, water especially, but also loose tailings or mud-like tailings, and avoid those mobile materials. In some cases, we can have those materials stored below grade, and then you've got geologic containment, and in most cases, there's very little risk of catastrophic failure there. But we find we almost always want to start storing some mobile materials above grade behind dikes. And if we truly want to reduce our catastrophic dam failure rate, we need to avoid that situation. Another curious one that I've spent a lot of my career on, people want to build wetlands and lakes on tops of tailings landforms. And geotechnical engineers hate water on slopes, water behind dams in the long term. We sort of take a blood oath to go and drain any puddles that form and that. But the biologists are saying, no, to have a good landscape, we need wetlands, especially in oil sands, but in a lot of other mining environments, especially temperate environments. And oftentimes anyway, there's residual ponds or pools due to settlement or just water collecting and stuff like that. So the cartoon here provides a tool for you to use. This is written up in the SEMA Wetland Manual from 2012, where we introduced the notion of a geotechnical critical zone and a geotechnical buffer zone, shown in the red dashy lines here on the on the slide. In the critical zone, and these are just constructs, in the critical zone, we never want to have any water ponding. So we're going to do all that we can in that sort of X zone, the outer zone, that even major storms or long-term wet periods, that we just can't have any water ponding near the dike crest. And so to do that, we have inwardly sloping slopes. We build it up. We make sure that there's just no way that if the pond grows, it can flood into that zone. And that ends up being fairly easy to do, but ends up meaning that your upstream or your crest of your dike, instead of being 10 meters wide or 50 meters wide, may end up being 300 or meters wide or more. How do you pick where that line is where the art comes in. We often pick that as being being controlled by seepage. We don't want the water table to get too high. We might pick it for erosion. We don't want wave erosion affecting the upstream crest. In a lot of cases, we're picking it as a piping criteria. We know that if we keep down around a 5% gradient between the pond and the toe, that piping is highly unlikely to occur. And so you can extend a line at 5% from the toe up to that geotechnical critical zone. 5% is 20 to 1. That's a pretty flat slope, but this is all part of the design. The buffer zone is a little different. That's between the X and the Y. And that's where we argue that we don't really want water ponded there permanently, but if you had a probable maximum precipitation event or probable maximum flood, or even say 1,000-year flood or something, that if it flooded into that zone and was there for a few months, that might be okay, that you wouldn't get all that much erosion, that it wouldn't have enough time to fully affect the steady groundwater flow patterns, seepage flow patterns. And so we set that area somewhere in there. So there's a lot of art that goes into this, and we're hoping that we can share some experience, get more guidance in that. We've used this on a half dozen projects, and it's worked out fairly well. Soft tailings, some of you'll know, is one of my favorite things to work on. Soft tailings are those tailings that are so weak that you can't get out with them with normal mining equipment. It's a term that I coined back in '99 when we started working on soft tailings at Syncrude, and we had a great big conference in Germany with about 100 people from around the world, each with soft tailings problems. I think we're coming to the point where we really ought to avoid producing soft tailings. I know some of your research will be involved with paste tailings or co-disposal tailings, but stuff that's hard to traffic and potentially mobile is pretty tough. So we should be trying to avoid or minimize that as much as practical. Sometimes it's not practical. The cartoon here shows 5 or 6 ways of capping soft materials, and these require people to write big checks. It's typically the cost of reclaiming, say, a tailing sand beach versus capping and reclaiming soft tailings. It's typically about 10 times the cost to do. Oftentimes these soft tailings cost upwards of $1 million per hectare to reclaim, to stabilize and reclaim. And so you need to be able to write the checks. We can do it, but it needs to be designed in from the beginning. We're about halfway through these problems and solutions. The next one is on to Nilsha Slingerland's work. Here, these are pictures from her thesis, sand dam erosion. When I was doing my original research at the U of A in 1996, I went out to about 77 mine sites around the world and have added to that numbers up to about 110 now. And I noticed that tailing sand dams, which are one of the hallmarks of the industry, are really, really difficult to reclaim, especially the downstream faces, especially stopping erosion. Typically, we put a 20 centimeters or up to 1 meter of cover on and vegetate it well. That's not too hard to do in the boreal. It's quite difficult to do in the semi-arid and arid parts of the world. And in some cases, we promise zero erosion. In some cases, we promise erosion similar to rates in the other areas. And you can imagine if you do get a gully through your cap and into tailing sand, which is usually a non-cohesive silt or sand, fine sand, that the erosion is really strong. And so it's not really clear that we can reclaim these well. People have had a certain amount of success. Sometimes it seems to work out in practice better than in theory. But where Nilsha has really contributed to this is with her work on modeling the erosion. Erosion models are extremely difficult, they're very complex, but she found a way to tame them and test them in the field. And this particular photo shows a bunch of different ways of organizing the drainage on your downstream dike face. She looked at benches, she looked at continuous slopes, she looked at something called katina, where the slopes are very steep at the top and flattened down to the bottom, more like a normal hill slope. She looked at putting in drainage and different things like that. So the answer then to the sand dam erosion concern is either to avoid sand dams and build them more like rock-fill dams or earth-fill dams, or to use good design on your downstream faces. Next slide. We worry about the longevity of the landform and typically don't declare what we're doing. I'm going to offer up that we should declare a service life, and there seems to be some consensus for tailings as being a 1,000-year service life. We used to promise that they'd be good until the glaciers came back someday, or they'd be good forever. If you wanted to apply your engineering or geologist stamp to that, that gets pretty tough pretty fast. In the United States, the uranium mine tailings capping work that was done in the 1980s, they said, we'll design this for 200-year service life. We'll have an eye out to 1,000, but we'll only promise 200. And they end up putting huge riprap, crushed rock and boulders on top of their tailings facilities to limit erosion, making them pretty much useless for anything else. And even then, it wasn't always successful. But where we get into this debate is as we put the tailings out, the tailings particles will tend to weather and change. That we'll get water flowing through the system, which may clog some of the internal drains or cause certain, with precipitates or biofouling, or if you've used some geotextiles, they're way out over time. Even bituminous membranes, BGMs, they likely have a service life. So I think or if you're worried about long-term erosion, like Nilsha's work has shown, and Haley Schaefer has picked that up at the university and taking that to the next step, looking at the long-term performance of dams and that. And if we can kind of at least settle on a finite service life, and I'm suggesting, and I think it's emerging, that 1,000 years is coming out. Some work on why 1,000 years is a good number needs to be done. Maybe it's longer, maybe it's shorter, but what can we reasonably offer up as a design team? Climate change is a big deal for landform design. I used to ignorantly kind of think, well, we're designing for the PMP and PMF anyway. What does it really matter that we're going to get bigger storms or more water or less water over time? We're already designing conservatively. But it's really interesting. There's so many things that climate change is affecting. And Nilsha's work in particular highlights it nicely, where her erosion modeling showed that if the area got drier with time, then there would be almost like a tipping point where the vegetation would change and wouldn't prevent as much erosion. And all of a sudden you had 5 times as much erosion as you would have had without the climate change, at least according to the models. But there are a bunch of tipping points that we're finding with earlier spring melts, lack of ice, lack of frost, all sorts of things that are coming up in the global climate change. So miners are finally, in the last few years, recognizing this, and we're learning about how to build it into our landform designs. been hinting at this a couple times in the lecture, the long-term longevity of internal dike drains. Years ago, we would almost always put a great big gravel drain underneath the toe of our dam. Casa Grande shows us how to figure out analytically. Had grad students run all sorts of cases in the 60s and came up with the plan for toe drains and triangular toe drains, blanket toe drains. When Syncrude built its dikes in the oil sands, we had gravel filter drains within the tailings sand dikes to control the water table. But over time, most of the mines have drifted to having sock slotted pipe, so PVC or other kinds of pipe with slots in it and surrounded by some kind of geofabric to filter out the solids from getting into it. And those pipes might last a couple hundred years, or they might only last 50 years. The clogging and general disintegration of the fabric is a concern. And so any dike with these geosynthetics in it will degrade. We might think, oh, there's no pond there anymore, we don't have to worry about the water table. But it turns out that net percolation from rainfall, as Daryl's shown here, will keep the water table somewhat elevated. And so in this case, we're showing, as the drain packs it in, the water table moves up to the top, and then you can see the downstream face has got some slumping and some gullying, and you may even have geotechnical instability with a rising water table. So these are all things that we need to think about in design. We may, there's sort of two aspects of this. One is to not use these kind of geomaterials, instead go for more natural materials. They still may clog, natural gravels and sands still may clog in that, but their longevity should be much better. Or use a fail-safe design such that you can reasonably assure yourself that even if the drains fail and the water table comes up sometime in the future, that you still have your adequate factors of safety and that there won't be too much erosion or poor material getting into the soils at the toes of your dikes. Getting on to poor seepage water quality, usually tailings poor water quality is pretty lousy at most mines. Oftentimes there's acid rock drainage. It'll be elevated metals in that. It tends not, tailings seepage tends not to be as bad as waste rock dump seepage, because the tailings tend to be less permeable and emit less water and can usually mostly control the oxygen getting into them, so the acid rock drainage is not as bad. But in some sites it dominates, especially where we built the tailings down in the river valleys on top of old rivers and the aquifers that creates. So what is a landform designer to do with managing the poor seepage water quality? Well, there's a bunch of different strategies here that come up every week in my practice, except for the first one. The first one, improve process water quality. So most landform designers, most geotechnical people as well think that, well, whatever the water quality is that comes out of the mill, that's just what it is. There's nothing we can really do about it. There'll be reagents in it left over. It's going to have whatever you've picked up from the mine and the acid rock drainage and all that kind of stuff. But actually we do have choices. And this particular scheme, I don't know if anyone will ever adopt. It's one of my favorite, freshwater tailings. And so that says to put your tailings through, if you still want to slurry your tailings, but you don't want the bad water, that you could use some kind of filter press or filter belts to suck out the bad water, and then you could bring in river water and you have fairly fresh water to send it out. That's pretty expensive, and if you're going to all that problem of sucking the water out, maybe you just want to truck or convey your tailings. But this is to highlight the point that we do have choice on our water quality, and this in the extreme case. The other case is where, when we were working in the oil sands, for instance, there was a big push for acid lime tailings. So you'd either bring the tailings up to pH 13 or down below pH 5 as a way of controlling segregation. This was early non-segregating tailings research in the 80s. we had to put our foot down and kind of say, look, we just can't manage pH 13 water in the landscape. We just can't leave it at that. It can be no higher than, we picked a number of 10, a pH of 10. Really, you'd like it closer to 7 or 8 in most cases. But you do have a certain amount of control about what the water quality is in the tailings. Failing that, you can put on good covers, and Michael Kane and the gang have written a couple guides on how to do that. You can use hydraulic barriers. So this is where you would be pumping, collecting and treating from the toe, reversing your hydraulic gradients so you're not allowing the seepage plume to escape in the groundwater beyond the toes of the dikes. The collecting and treating is one of the most common methods, especially in metal mines. And everyone worries about how hard it is to treat the water treatment plants and the costs associated with those. But actually collecting the water and just getting it, not having the seepage bypass your pumping system or ditching system is sometimes harder than the water treatment. Getting down to the last couple slides here and approaching the top of the hour. A lot of mines have difficulty with their tailings with outlet spillways. There's kind of two schools of thought out there. In all cases, we want to build them into a sound foundation. This is a picture from a mine in British Columbia, and here's a spillway cut in bedrock, kind of rough, but small mine. Tailings pond can go out through there. There's no way that water is ever going to erode down into that. It's safe and stable. A lot of mines, though, don't have bedrock. They're either in tropical areas where there's deeply weathered bedrock and not fully resistant to erosion, or they've built up ring dikes or other facilities that are built out of sand. And now we're faced with putting a spillway down the slope of a dam made out of sand that likes to have piping, and that it's highly erodible. And here it's supposed to pass typically the probable maximum flood. These spillways can be 50, 60 meters wide in design, 10 meters deep, a kilometer long, pretty tough. And so one of the how-to solutions is either make sure you got some bedrock nearby, or when you know where you'll choose your outlet location during initial design, and let's make sure that we don't have tailing sand right in that section where we want the spillway to go. Could we build it out of clay or something compacted to 100% modified Proctor, some good dam section all the way through, there's just no potential of erosion out of your fragile spillway. Everyone these days wants to de-license their dams. Every jurisdiction has a little bit different word for this, but this is doing enough. This is where the turning it into a landform, alas, came from. But we don't want to be doing dam safety inspections every year for the next 1,000 years, and dam safety reviews every 5 or 10 years. We don't want to be doing daily inspections of the pond and all the things that we do for normal tailings dams. We want to design and construct them so they can be de-licensed. And this busy slide is from the 2014 How to De-License Oil Sand Tailings Dams. And there's additional work that Canadian Dam Association has done on mining dams on this. It's really tough if not planned in advance, and it's not quite clear. The regulator in a lot of cases will sign off that it's no longer a dam, that's just turned into essentially a mine waste facility with no chance of a catastrophic breach. But there is guidance on how to do this, and it's being tested around the world. And it is so much easier if you've designed it from the beginning. Managing your liability into your long-term. Most miners, I think, still think that they're going to walk away from their sites, that they'll build them robust enough that they won't need any maintenance for the next 1,000 years. That's pretty much a pipe dream. Mines will be taking care of their sites, at least to some level, for years to come. So let's try and minimize that rather than eliminate it. Use really good, robust design and embrace the aftercare. And Daryl's picture here shows some of the sort of events going on in monitoring and maintenance of a well-built landscape. Last couple slides here, not enough financial assurance. Almost no mines, when they close, have enough money in the bank to actually go and reclaim. what they do, what we find is that the estimates of, or the amount of bond money that's held by the government, should it default to the government, is typically about 10% of what it actually costs. I'm working on the Faro mine these days in the Yukon. Some of you will know about. The original bond was $28 million. The most recent cost estimate to reclaim that site is $1.5 billion. And so there's two aspects. One is that the cost estimates are usually wildly optimistic, and the government hasn't collected enough bonding even for the lowball costs. And so a couple solutions for that is working towards getting independent cost estimations rather than just the mines providing them, and a more rational bonding requirements so that there's money available. I've never heard a regulator say, oh, don't worry if they go bankrupt, we got lots of money, we can take care of that. I actually don't know of any mine that's paid for its own reclamation. It's always a sister mine or ongoing operation that's required. So last slide here is focusing on design. This is wrapping up all the things that we've been talking about here. In a tailings facility that's being built into a valley here, and just sort of working through counterclockwise from the pond at number one, is beginning with the end in mind. In this case, someone has wanted to have a long-term pond and have some fishing in it. So implies certain water quality, implies certain physical stability, implies certain water balance. We're going to keep the clean water clean, and number two, with diversions. We don't want the clean water running off the slopes from mixing with the dirty water in the tailings, typically. Number three, we're going to build robust outlet, and then we're going to make sure that all our tailings that we pour out there or place out there is directing water towards the outlet. We're going to locate the spillway and bedrock, number four, that we talked about. We're going to control the runoff with ridge and swale topography at 5. This is keeping it out of the geotechnical buffer zone and the ponded water out of the critical zone, even during massive events. Number 8, we're going to create a nice wide crest sloped upstream as part of the geotechnical critical zone. We're going to build a watershed berm right at the crest. So if we did get any water, that it's not going to go over the crest and cause a lot of erosion. So we build a 2-3 meter high berm there. Number 10, we're going to design the downstream face to control erosion. This is from Nilsha and Haley's work. Plan for contingency seepage control measures. They're number 11, so we want good water quality, but if we need it, we might have to put in a pumping system and gather up that seepage water. Number 12, we're going to offset infrastructure from the toe, so if there is some erosion deposition, that we're not impacting the infrastructure. Part of the Global Tailings Initiative, we're trying to get almost everything that we can out. You know, we often put office buildings or laydown areas right at the toes of dikes, and where mines are now relocating those kinds of facilities for a safety thing. 13 is providing good access. So, you know, the old paradigm, we're going to walk away from this. We're going to get rid of the roads, but actually we want to leave some pretty good roads into the site so we can monitor and maintain. Number 14, we're laser focused on meeting objectives for water quality and water quantity downstream. So those are some of the things to focus on design as we go through. So I'd like to encourage, especially the students, but everyone listening here, to join the Landform Design Institute. There's a $10 option for an annual membership for students, and you can go to landformdesign.com to sign off. Individual memberships are also available, and the student memberships and the individual memberships all get the same benefits to it. If you don't want to join like that, I'm hoping that you'll at least join our mailing list. We've got about 700 or 800 people on the mailing list, and we send out a quarterly newsletter with what we've been up to and what we're planning. We've got some corporate memberships. You can see the logos here, and we're going to be seeking some sponsorship to put together all these good books. You may find yourself involved with production of some of these things. We haven't quite figured out the cost model, but there'll be some paid research being done over the next 10 years in producing these how-to guides that we've been hinting at here during the presentation. Contact information, if you're looking for Daryl to do some drawings for you here, he's based on Gabriola Island near Nanaimo, BC, and he'd love to work on your projects. And if you've got any questions for me, we've got some time here coming up in a moment, but oftentimes there's one or two questions that come up after. As an adjunct professor in your department, I have a duty to offer and work with you on these things, but I'd love to anyway. It's actually the best part of my job. And so feel free to reach out to me by phone or email, and let's get a conversation going. So I'll turn it back to Kevin here. Thanks for allowing me to present to the time today, and I'm hoping there's still time for a couple questions.
Yeah, definitely. I mean, Lang will be the one doing the Q&A. So if Lang, you want to jump on and ask a couple questions to Gord here, that'd be great.
Sure. Thank you for the great presentation, Dr. Gord McKenna.
Thank you.
We appreciate your time for spending with us and sharing your expertise of global tailing management with us. And I love those head sketches you used in your illustrations. And yes, as Kevin said, I'm the moderator for the Q&A sessions. We welcome everyone to put your questions in the chat if you have any. As far as I can see now, we have two questions. One is from Dr. Jen Hutchinson. She is concerned about how do you balance the use of saturation to mitigate environmental impacts due to oxidation of sulfides. For example, versus the need to reduce the mobility of the tailing against potential catastrophic failure. You have any recommendation on this?
Yeah, so the sort of two aspects. So one, if we can pick on, say, the Kemess mine as an example in central BC, they've got a closed tailings facility with highly sulfidic tailings. And they wanted to limit the oxygen getting into the tailings, and they found the best way was to create a huge tailings water reservoir on top of the tailings. And in the slide I'm showing here, it would be as though that pond that's there extended all the way back to the back of the reservoir and all the way to the dam crest, and they've left behind a very high dam crest. And so engineers, especially geotechnical people, really worry about leaving a huge pond behind a dam for the next 1,000 years or longer. You know, it's going to see all weather, it's going to see all earthquakes, it's going to see all storms and different conditions, and we're going to maintain that and keep the beavers from blocking the spillway and all those things. That society will take care of that, but chances are there'll be some periods of time for tens of years or maybe longer. We think about things like civil war, we think about society breaking down, or just having no money for a long time, or just kind of losing focus. And so then the risks of a breach come right up. And so the geotechnical people would say, well, we just can't have water behind dikes like that. It's just not safe enough. And then the environmental people say, oh, well, we need water because we need to keep it saturated, as Jean has mentioned, to limit the oxidation and protect the fish downstream from pH2 water. And some recent interviews I've been doing with experts around the world, they kind of point out that we need to get away from this dichotomy of geotechnical versus geo-environmental, and not really frame it that way and say, no, this is our chances to work together. And there's some novel concepts coming out with keeping saturated soil layers rather than a big pond, or keeping the tailings saturated and having it built in. Michael Kane's been doing quite a bit of work with this. Lee Barber's been involved, probably others on the call here today. Just how these will pan out and just how they'll work, it's not a slam dunk and it's not very easy. And is it going to be reliable? I'm really hopeful, but I think we need to find a way of avoiding the situation if we can. There's quite a lot of mines that desulfurize their tailings. So they run their tailings through a desulfurization system and concentrate the pyrates. And in some cases, they can even sell the pyrite. That's hard to do for an existing facility, easier to do for a new facility. Sometimes the regulator demands that. So kind of a source, getting rid of the source or some kind of source control. But I think we all feel a little uncomfortable having water caps above high dams. So Dr. Hutchinson points out a really tough problem that's going to need to be solved here. Each mine solves it its own way. There's been some positive successes, but I think we need a little bit more guidance to not get ourselves into this in the first place. Another question?
Thank you so much for your explanation. And the next one is from Dr. Alain. She is asking, like, you lead the charge on the actually propose this concept of let's try to get it right at the planning and design stage in terms of the reclamation and the closure. She's just curious to hear what's your thoughts that you would have done differently if you had to embark on this quest all over again. What advice you would like to give to the next generation engineers who are faced with resistance but trying to utilize some game-changing tools to improve things from the beginning?
Well, that's a good question. I think what has surprised me in the last is we put together this position paper for the Landform Design Institute, is we found that even after 25 years and of doing this in the field and doing all these courses and teaching and talking and arguing and enjoying good coffee and beer over it, that we're still struggling a bit on some of the fundamental definitions and interpretations of, what is a landform and what scales is this working at and how best to communicate it. And so, and what has come out of our discussions on this just recently, and sometimes we have to remember what we'd done before, and we talked a long time ago, years ago, about the need for this integration, and then we just kind of, we've always promoted that, integration of the different ologists on the landform design team, integration with mine management, with the regulator, with the operators in the field, with First Nations, local communities. But I think it's hard to answer such a broad question, but the number one thing I think to leave with, or two things to leave with the students today especially, is this beginning with the end in mind and really embracing that. It's not lip service. This is full on making good decisions up front. It turns out 80 or 90% of the decisions that are made before mining even begins. The last decisions are retrofit and expensive decisions in the field. So number one, beginning with the end in mind, and number two is this integration. Just look every opportunity you can for integration. I know the University of Alberta teaching and curriculum here is very strongly focused on the integration and making sure that people leaving the university have a good handle on groundwater and surface water, on soil chemistry and a bunch of these things. And then as you go into your career, seeking out opportunities to work with the soils, veg and wildlife people, understanding where they're coming from and what they're trying to do, working with First Nations, working with regulators, really integrating. So just keeping integration number one in your mind, I think will help all of you in your careers as you go through. Even if you're not doing landform design, you might be working on foundations, or you might be working on remediation projects or pipelines, all the things that we get involved with. And any chance you have to cross-train and work with the local communities and work with other specialists and really, really integrate, I think that's going to be one of the major aspects of your careers. Good question.
Good answer, Dr. Gord McKenna. I think that concludes our presentation for today. And thank you again for spending time with us and giving such amazing presentations. And so I would like to turn this to Kevin. Does Kevin have any question or announcement on this?
No real announcements. This was our last presentation of the semester, so we'll be restarting in the new year, sometime in January. But thank you very much, Gord. That was a fantastic presentation.
My pleasure. Thanks for the chance today.